Let's just dive right into our discussion of Section 13.4 on normal distributions. I want to begin by talking in particular, though, about frequency distributions and histograms. Large sets of data are often displayed using a group frequency distribution or a more visual method, a histogram. For instance, an internet service provider has installed new servers. To estimate the new download time that subscribers will experience, the ISP surveyed 1,000 of its subscribers to find the time required for each subscriber to download a particular file from an internet site. Here are the results of the survey in table form. Notice the grouped part of this. This table is called a group frequency distribution because the column on the left is grouping the download times into intervals. It's showing how frequently certain events occurred. That left-hand column that's grouped into intervals 0 to 5, 5 to 10, and so on, each of those groupings is called a class. In this particular case, if you count them, you'll see there are 12 classes. For example, if you look at the 35 to 40 class, the left-hand boundary is called the lower class boundary. The right one is called the upper class boundary. So here, 35 would be the lower class boundary, 40 would be the upper class boundary. A data value that lies on a common boundary is assigned to the higher class. So if it says 40 to 45, an actual data value of 45 would go in that class. The graph of a frequency distribution is called a histogram. So if you want a more visual look at this data, you can do this. You basically put bars to represent the number of subscribers. So the heights of the bars tell you how many subscribers experience that particular download time. That's called a histogram. Let's pull this table in and continue looking at it. I can change from just the raw number of subscribers and instead look at the percent of subscribers. If I take the table on the left and change nothing except the number into a percent, I go from a group frequency distribution to something called a relative frequency distribution. Group frequency on the left uses the raw numbers. Relative frequency on the right changes those to percentages. You can also do a visual representation of the relative frequency distribution as well, where the raw numbers on the vertical axis are changed to percentages. So if you look, the 20 to 25 class says there are 15.1% of subscribers. So if you go to the 20 to 25% class and go up to the height of that bar, you'll see that it corresponds to the 15.1. All you're doing is taking the table and turning it into a picture. You're turning it into a picture of the data using the height of the bars as the percents. One advantage of a relative frequency table is that it makes answering many probabilistic questions about the data easy. Let's again stick with this same example. Because download times are grouped by percent of subscribers, we can make probability statements such as, if a subscriber is chosen at random, the probability that the subscriber will take at least 35 seconds but less than 40 seconds to download the music file is 0.149. You see where that comes from? 35 to 40, at least 35 seconds but less than 40 is 14.9%, which as a decimal or a probability, move the decimal place 2 places to the left, would be 0.149. What is the probability of a randomly selected subscriber taking less than 20 seconds to download a file? Well, you look, 0 to 5 is less than 20 seconds, 5 to 10 is less than 20 seconds, 10 to 15 is less than 20 seconds, and 15 to 20. So if you take all the percentages that satisfy the statement that it's less than 20 seconds and add them up, you want to change them from a percent to a decimal. So you move the decimal place 2 places to the left, add them up, and you'll see that the probability is 0.158. You could have added up the numbers and then moved the decimal place to the left. You'd get the same result. How about this one? What is the probability of a random subscriber taking more than 20 seconds to download a file? Since you know the percentages add up to 100%, or as a decimal, the probabilities add up to 1, you can just take the answer you got before, which is the 0.158, and subtract it from 1. That's easier than adding up the rest of the numbers, but if you did add up the rest of the numbers, you would get the same answer. Of course, the questions can also ask for answers involving percents instead of doing probabilities. So, for example, the percent of subscribers requiring 25 seconds or more for the download, you just go and you'd look at all the ones requiring 25 seconds or more. That would be starting at the 19.2 number, add them all up, and you'll get 69.1%. So if it asks for a percent instead of a probability, you don't have to move the decimal place 2 places to the left. As a percent, it'd be 69.1%. As a probability, it'd be 0.691. So you just need to be careful about how the question is worded. One of the most important statistical distributions of data is known as the normal distribution. This distribution occurs in a variety of applications. I won't mention them all, but measuring errors, as they say here, the weights of newborns in the hospital, lots of things follow a normal distribution, hence the name normal. The lifetime of an electronic component, maybe a light bulb, things like that. A normal distribution forms a bell-shaped symmetric curve about a vertical line that goes through the mean of the data. I'm sure that each of you have seen this at some point. But a typical normal curve would look like this. The one displayed here has a mean of 5. The Greek letter mu is our symbol for mean. Let's look at some of the properties of the normal distribution. First of all, the graph is symmetric about that vertical line through the mean. If you were to cut that graph in two, right down that vertical line, the left half would fold right over on top of the right half. That's the symmetry. It turns out that the mean, median, and mode are all the same for a normal distribution. The y values can be thought of as percents, even though they're expressed as decimals. So a 0.15 would be a 15%. A 0.27 would be 27%. They're written as decimals, but they can be interpreted as percents. Symmetric areas under the curve are equal. So if you've got an area, say from 3 to 4 as pictured here, it's going to have a corresponding area on the other side that will have exactly the same area, and you measure it the same distance away from the mean. And the total area under the curve is 1, which represents 100% of the data. Look at this. In this normal distribution, the area of the shaded region is 0.159 units. This region represents the fact that 15.9% of the data are greater than or equal to 10. And because the area under the curve is 1, the unshaded region under the curve has an area of 1 minus 0.159, which is 0.841, which represents the fact that 84.1% of the data are less than 10. Remember, the total area of the curve adds up to 1, so those two numbers have to add up to 1. The following rule, called the Empirical Rule, describes the approximate percentages of data that lie within 1, 2, and 3 standard deviations of the mean in a normal distribution. This is just a device that helps us get a ballpark answer for some common type problems. The Empirical Rule for a normal distribution says that 68% of the data lie within 1 standard deviation of the mean. Notice if you look at the mean mu, if you move to the left 1 standard deviation, you have 34% of the data. If you move 1 standard deviation to the right, you've got another 34%, approximately, and 34 plus 34 is 68. But if you go 2 standard deviations away from the mean, you pick up another 13.5 on the left side and another 13.5 on the right side, and if you add up all those numbers, you'll get 95%. If you go yet another standard deviation from the mean, you pick up an additional 2.35% approximately on the left and another 2.35% approximately on the right, and that adds up to about 99.7% of the data. What's left over in the tails, you split between the left tail and the right tail, and it turns out to be about 0.15%. And if you add all those numbers up, within rounding error, you'll get 100%. That's the empirical rule. Let's use it here. A survey of 1,000 gas stations found that the price for a gallon of regular gas could be closely approximated by a normal distribution with a mean of $3.10 and a standard deviation of 18 cents. So putting that on the actual normal curve, I'm saying that the mean is 310, standard deviation is 18 cents. If I want to interpret that in terms of the empirical rule says, for one thing, if I want to go one standard deviation from the mean, that would be like taking 18 cents away from 310. That takes me to the left of the mean by one standard deviation. That would be at a price of $2.92. Then move one standard deviation to the right. That means I'd add 18 cents to 310. That would take me up to 328. One standard deviation away from the mean would be anywhere between 292 and 328. If I want to go two standard deviations from the mean, I start at 292 on the left and take away another standard deviation, which means I subtract away another 18 cents. That would take me to 274. Then I move to the right and I move from 328 another standard deviation, which means I add another 18 cents to 328, and that gets me up to 346. So to be between two standard deviations from the mean, the price of gas would be between 274 and 346. If I wanted to go three standard deviations from the mean, I'd keep up the pattern. I'd take another standard deviation of 18 cents away from the leftmost one, which is 274. That would take me down to 256. Then I'd move to the right and add 18 cents to 346, and that would give me up to 364. So any price between 256 up to 364 would keep me within three standard deviations from the mean. So if you saw a gas price above 364 or below 256, that would be highly unlikely. It happens only in a very small number of cases if the data is normally distributed. Let's answer some questions. How many of the stations charge between $2.74 and $3.46 for a gallon? If you're going to use the empirical rule to answer this question, you've got to look at what we just did and analyze it. So if you look at 274 and 346 and look at all the percentages between those two numbers, you get 13.5 twice and you get 34 twice. In other words, add up all those percentages between 274 and 346, and this is the nice part of the empirical rule. Even though it's just an approximation, it's a pretty good approximation, and it's easy to do once you know these basic percentages. So if you add up those percentages, you'll find out that about 95% of the stations would charge in between those two numbers. Now it said how many, so now you got to look back and say, well, there are 1,000 gas stations surveyed, so you'd have to take 95% of that. 95% is 0.95. 0.95 times 1,000 gives you 950. So about 950 stations would be expected to charge between 274 and 346. How about this? How many of the stations charge less than 328 for a gallon? So again, you look back at the empirical rule work that you did, and if you want to say less than 328, that means you start at 328 and move all the way across to the left. So you pick up every percentage to the left of 328. Now you could just add up 0.15%, 2.35%, 13.5%, 34%, and 34% and do it that way. But you could also notice that if you just look from the mean all the way to the left, you know those numbers are going to add up to 50%. So it'd save you a little time if you just realize that from the mean all the way back to the left, when you add those numbers, you're going to get 50%. So really all you have to do is add that 34% that wasn't included, and that'll get you there faster. 84% is 0.84. 84% of 1,000 then would be 840. So you can expect about 840 of those 1,000 gas stations to have gas that sells for less than $3.28 per gallon. How many of the stations charge more than $3.46 for a gallon? Well, again, looking at your chart, more than 346 means to the right of 346, and you can see that there are just two numbers out there, 2.35 and 0.15. If you add those up, you're going to get 2.5%. You could also use a subtraction thing and say, well, I know that it's going to be 50% to the right, and I can take away the 34 and 13.5, and that would give me the same answer. So there's almost never just one way to do this, but you choose which way makes the most sense to you. But just be careful that you've pictured the correct group of numbers to add up. In any case, 2.5% is 0.025, so that would be times 1,000, that'd be 25. So you can expect there would be about 25 stations selling gasoline for more than $3.46 per gallon. If you do a lot of work with statistics, you'll see that this 2 standard deviation case pops up a lot. So I thought I'd pull it out and take a particular look at that one. If you think about it, the 2 standard deviations, I just shaded the area red there. That includes the 2 13.5 percentages, and it includes the 2 34 percentages. That's 2 standard deviations away. And if you add those up, that's the 95% region. So about 95% of the data in a normal distribution is going to fall within 2 standard deviations of the mean. What that means is there's another 5% left, and that 5% left has to go between the 2 tails. So that 5%, you get 2.5 on the left and 2.5 on the right. So this 95%, this 2 standard deviation case comes up and is used so much in statistics. I thought I would just give you a visual on that one. That one is used a lot. It also gives you another way of answering the last question about how many of the stations charge more than $3.46 for a gallon. Because if you go back and put those numbers on this simplified version of the normal distribution, you'll see that that 346 hits right there where the right tail begins. So if you're looking for more than 346, you can see that it's going to be 2.5. And that's what we got when we calculated earlier. Instead of remembering the empirical rule as a bell curve, I usually think of this when I think about the empirical rule. There is a whole curve that keeps going up above it, but the important numbers comes from this slice at the base. So I don't know how much of this you want to actually memorize, but if you memorize those percentages, it really puts you ahead of the game in answering questions about the empirical rule. Let's look back again at this gas station survey exercise. A survey of 1,000 gas stations found that the price for a gallon of gas could be closely approximated by a normal distribution with a mean of $3.10 and with a standard deviation of 18 cents. We've been working on that one for a while. I want to add one more thing. How many of the stations charge more than $2.92 for a gallon? Well, again, I need to find those prices at each standard deviation board. We've already done that, so I'm just going to bring them back. So this is what we did earlier. So if I want to look at how many stations charge more than $2.92 a gallon, I want to find 292, and then I want to go greater than. So everything to the right gets counted. So if you add up all those percentages, you're going to get 84%. You could have done that easier by noticing that if you start at mu and go to the right, you're going to get 50%, and the only one that wasn't counted was the 34% to the far left. If you take 50% and 34%, you'll also get 84%. So the better you get at this, the less time you have to spend adding up numbers. You can probably do things a lot easier if you just think about things like that. To find the actual number of stations, I have to take 84% of 1,000, and that would be 840. Often percentages that we need don't match those of the empirical rule. If that's the case, we can make use of a distribution called the standard normal. The standard normal distribution has to do with the distribution of the z-scores. We talked about those earlier, so I'm not going to make a big deal about that. But remember, with z-scores, you take the original data, subtract the mean, divide by the standard deviation. If the original x values are normal, the z values that result from that calculation will also be normal. And graphically, I'm not going to make a big deal about this, but if you look at the original normal distribution on the top right with x values, you can convert it using that z equals x minus mu over sigma to a standard normal distribution, and that standard normal distribution is going to have a mean of 0 and a standard deviation of 1. So what you're doing is you're changing the original distribution to a new distribution that always has a mean of 0 and a standard deviation of 1. Now, you may not appreciate how important that is, but that's extremely important that we're able to do that. One implication of being able to do that is we can take one table and table values of the standard normal so that we can look up all sorts of answers to probability questions involving normal distributions. And you're going to see that as we move forward. One of the most important things to note now about this standard normal curve is that the total area under it is 1, as it is with any normal distribution. The area is always equal to 1, which represents 100% of the data. And for standard normal, the standard deviation is 1. The mean is 0. But the total area being 1 is extremely important to us. Also notice the symmetry. If you take something and cut that graph right down the middle through z equals 0, the left half and the right half are symmetric. So if the total area is 1, if you cut it in half, on the right side you've got a 0.5, which is half of 1. If you go to the left and cut a slice, you've got a 0.5. And if you take 0.5 and 0.5, of course, you get the total area of 1. The symmetry is extremely important. For example, to find the area under the standard normal curve from z equals 0 to 1.44, we just look the value up in the table. Remember, the table gives the area from 0 to any positive z value, and this perfectly fits that description. We're starting at 0 and we're going to 1.44, which is a positive z value. So you simply find 1.44 in the z column, and I'll blow this up a little where you can see it better, and you'll see that the corresponding area is 0.425, and that's all there is to it. So in the simplest case, where 0 is the left boundary, you simply look up the z value, find the corresponding area, and you've got it. The standard normal distribution is symmetric about the mean of 0, so we can also use that table to find areas to the left of the mean, even though the table doesn't give any negative z values, and the way you do that is by noting the symmetry. For example, if I wanted to find the area under the normal curve from z equal minus 1.44 to 0, and again it's pictured up there now, that z value would be negative 1.44, and there are no negatives in the table. However, I know because of the symmetry that the area from minus 1.44 to 0 is going to be exactly the same as the area from 0 to 1.44. So I still can use that same number and just get 0.425, even though there is no negative z value in that table. I'm using the symmetry of the situation. The area to the right of a positive z value or to the left of a negative z value is called the tail of a distribution. Let's play with those a moment and see what happens. Suppose I wanted to find the area under the standard normal curve for a z greater than 1.44. It's pictured as being a right tail. It's to the right of 1.44. The table value doesn't give you the area to the right of a z. It gives you the area from 0 to z. But that 0.425 can still be labeled on that graph from 0 to 1.44, and I know because of symmetry that the area from 0 all the way to the far right is going to be a half. I'll find out by subtraction that the area that I'm looking for is actually 0.75. Just for practice, let's use the standard normal table to confirm some of the empirical rule probabilities that we used earlier, just for the fun of it. For example, let's use the standard normal table to show that about 68% of the area is within one standard deviation of the mean. Remember our empirical rule probabilities. If we want to stay one standard deviation from the mean, if you go to the left, you get about 34% of the data. If you go to the right, you get about 34% of the data. So as long as you stay within one standard deviation of the mean, the empirical rule says you should get about 68% of the area. If we actually look that up in the table, we have to look up 1, and 1 gives us 0.341. But remember, that gives us the area from 0 to the right until we get to 1. We have to double that if we're going to the left as well. But if you take 0.341 and add another 0.341, you get 0.682, which is fairly close to 68%. So the empirical rule is an approximation. It's a pretty good approximation, but you can see it's off a little bit if you actually use the values from the table. How about doing the same thing now to show that 95% of the area is within 2 standard deviations of the mean? Remember, the empirical rule says if you stay within 2 standard deviations of the mean, you're going to get 95% of the data. That's 13.5 twice and 34% twice. That adds to 95%. If you actually look that up in the table, if you look up 2, you'll see that it's about 0.477. But that's the area from 0 to the right until you get to 2. There's an equal area to the left going the other direction to -2, so that's also 0.477. And if you add 0.477 to 0.477, you get 0.954, which is about 95.4%, which again is close to 95%, which is the approximation that the empirical rule gives us. So you can kind of see the empirical rule is an approximation, but it's a pretty good approximation. Because areas under the standard normal curve can also be interpreted as probabilities, we can use the standard normal distribution to solve many application problems involving probability. For example, suppose a soda machine dispenses soda into 12-ounce cups. Tests show that the actual amount of soda dispensed is normally distributed with the mean of 11.5 ounces and a standard deviation of 0.2 ounces. What percent will receive less than 11.25 ounces of soda? How do you answer that question? First of all, we have to convert this to standard normal. These are values with the mean being 11.5. Remember, standard normal, which is what we have to look up in the table, has to have a mean of 0. And of course a standard deviation of 1. So we have to use the z-scores. So in this case, if we want to see what percent will receive less than 11.25 ounces of soda, 11.25 becomes the x value. And we want to subtract off the mean, which in this problem was 11.5, and then divide by the standard deviation of 0.2, which gives you a negative 1.25. Remember, we've got to interpret that now as an area. We want to know what percent will receive less than 11.25 ounces of soda. So thinking about that, if you put z equal negative 1.25 on the standard normal graph and you want it to be less than that, you're looking at the left tail of that distribution. Remember, you can't look up negative values in the table, but you can realize that the equivalent area going from 0 to positive 1.25 is going to be the same. So all you really have to do is look up 1.25 and you'll have the area to the right of 0 but to the left of 1.25. So you're still not quite at your answer because, again, to emphasize, the number in the table, that 0.394, gives you the area from 0 up to z equal 1.25. But you want the shaded area to the right of that. But remember, because of symmetry, all you have to do is subtract from 0.5 because everything to the right of 0 has an area of 0.5. So if you subtract, you'll find out that the shaded area, the area you really want, is the difference between 0.5 and 0.394, which happens to be 0.106, which is about 10.6%. So you can expect about 10.6% of the sodas to receive less than 11.25 ounces of soda. Also, because this percent can be interpreted as a probability, you could also say it this way: the probability of getting a cup containing less than 11.25 ounces of soda from this machine is about 0.106. Let's ask another question. What percent will receive between 11.25 and 11.7 ounces of soda? So the first thing you're going to do is change those to z-scores. We're going to use the standard normal table to look this up, so that the x values have to be converted to z-scores. So you'll take each one, the 11.5, change it to a z-score. We actually did that earlier, so I'm not going to emphasize that again, but it came out earlier to be negative 1.25. But now we also have to do it for 11.7. So if you take the z value for 11.7, you'll get 11.7 minus 11.5, which is the mean, divided by 0.2, which is the standard deviation, and that comes out to be exactly 1. If you want to look at that as an area, put it on the standard normal between 11.25 and 11.7. Those two numbers converted to z-scores become negative 1.25 and 1. The 11.25 taken to 0, and then the 11.7 takes you all the way to z equal 1. So we're looking for the area between z equal negative 1.25 and z is equal to 1. When an area crosses that z equals 0 vertical line, you want to treat it as two separate areas and add the results together at the end. So what we'll want to do is take one area at a time. So you've got the area from 0 to 1, you've got the area from minus 1 to 0. Let's look at the one from 0 to 1 first. That area can be looked directly up in the standard normal table by looking up z equal 1, and it comes out to be 0.341. Now let's go to the other side and do the other one. The other area has a negative z value, but because of symmetry, we can look up the positive z value and the area will be the same. So if you go to the table and look up positive 1.25, you get 0.394. So now we have both individual areas and we just have to add them together. 0.394 plus 0.341 is 0.735, or 73.5%. So we can expect that about 73.5% of the cups will receive between 11.25 and 11.7 ounces of soda. And again, because this percent can also be interpreted as a probability, we could also say that the probability of getting a cup containing between 11.25 and 11.7 ounces of soda from this machine is 0.735. What about this question? What percent of cups of soda do we expect to overflow? Well, remember, it's a 12-ounce cup, so overflowing would be for it to go over 12 ounces. So 12 is what we want to change to a z-score. So you plug it into your formula and say 12 minus the mean of 11.5 divided by the standard deviation of 0.2, and that comes out to be 2.5. We want it to be interpreted as an area under the standard normal, so we want it to be greater than 2.5. That's the overflow area. So look up 2.5 in the table and you get 0.494, but remember that gives you the area from 0 to z equal 2.5, but you want the area above 2.5, but because of symmetry you know that half the area is to the right of 0, so all you have to do is subtract 0.494 from 0.5 and you'll find out that about 0.6% of the cups will overflow. Or stating as a probability, we can say that the probability of a cup from this machine overflowing is about 0.006. Just as we can use z-scores to find areas under the standard normal curve, we can also reverse the process and find the z-score corresponding to a given area under the curve. For example, find the z-score to the nearest hundredth corresponding to 0.218 square units of area of the standard normal distribution to the right of z. You need to think about what that looks like. We're going to the right of z and we want an area of 0.218. So that's what it looks like. You're at a certain z value. You want the area to the right to be 0.218. Now we know that the areas in the table are from 0 to a certain z value, so it's to the left of that 0.218 all the way back to 0. That's what the table value gives you. But we want to look at the table and find the z value that produces that much area, but we first have to figure out what the area is to the left. And we know because of symmetry that there's half the area from 0 to the right, so if we take 0.5 and subtract away the 0.218 to the right, that tells us immediately the area from 0 to that unknown z value has to be 0.282 because 0.5 minus 0.218 is 0.282. That gives us the information we need to go to the table. But this time we know the area and we're looking for the z value. We've been looking up the z value and finding an area. Now we're looking up the area to find a z value. So let's do that. If you look into the table, you'll see that 0.282 as an area is associated with a z value of 0.78. So now we know the z value of 0.78 will produce an area from 0 to 0.78 of 0.282, which means that the area to the right of z is 0.218 as stated in the problem. Just have to think about it and go step by step. Let's do another. Find the z-score to the nearest hundredth corresponding to 0.206 square units of area of the standard normal distribution to the left of z. So this time they're telling us information about being to the left of z. We want to be 0.206 square units in area to the left of z. So if you think about this, that's an area less than 1/2 at the left. So that has to be a negative z value because you have to get up to 0.5 to even get to 0. You'd have to be bigger than 0.5 in an area to get past 0. So this area being to the left of z is clearly a left tail, and it's going to produce a negative z value. So that much we already know. We also know we can't look up anything that comes out negative for z from the table, so we're going to have to use our symmetry knowledge to produce the right answer here. But we want that z-score. If the area to the left is 0.206, then what is the area remaining from that z value to 0? Well, that's easy. We know by symmetry that half the area is to the left of 0, so all we need to do is subtract, and if we take 0.5 minus 0.206, we'll find out that the remaining area from that z value to 0 has to be 0.294. And now we know by symmetry that even though that is a z value in actuality that's negative, when we look it up, we have to look up the positive value and just make it negative using our knowledge of symmetry. So at this point, we've got to just look at symmetry from the picture and look up the positive value. The positive value for an area of 0.294 happens to be 0.82. We know that it can't be positive 0.82 because that would put it to the right of 0. Our symmetry, though, assures us that it's actually the same area, but it's to the left instead, so the z value has to be negative 0.82. We look up the positive, but we know we want the negative. So again, you have to just think this through. It's not difficult, but you have to remember what the table tells you and what you know from looking at the statement of the problem. So the corresponding z-score is z equal negative 0.82. Let's practice a little bit more. Find the area to the nearest thousandth of the standard normal distribution between the given z-scores, and here we're looking between z equal 1.24 and z equal 1.81. We know what the standard normal looks like, and when we say between, we know we're looking for the area that lies between the z value of 1.24 and 1.81. Look up the big value in the table, 1.81, and we get an area of 0.465. But remember, what you get from a z value when you look up the area is an area that goes all the way back to 0. So the answer is not 0.465. The area from 0 to 1.81 is 0.465. But that's too much area. We only want that smaller slice between 1.24 and 1.81. So what do we do now? Well, we also know that we can look up 1.24 in the table. and get an area that represents the area from 0 to 1.24, and that's the amount that we want to subtract away because that's the area that we didn't want. So if you look up 1.24, you'll see the area is 0.393, but that's the area we don't want. So we take the bigger area, 0.465, subtract off the excess area represented by the area from 0 to 1.24, and that leaves us with the area we're actually looking for, which is 0.072. So the area under the standard normal curve between z equal 1.24 and z equal 1.81 is approximately 0.072 square units. You can almost treat this like a game. You've got to figure out what things you can do to get the answer you want. Let's do another. A manufacturer of light bulbs finds that one light bulb model has a mean lifespan of 1,029 hours with a standard deviation of 80 hours. What percent of these light bulbs will last as follows? And in this particular case, we want to know what percent of the light bulbs will last between 850 and 900 hours. Again, we have to change those x values to z-scores before we can look them up, because the mean here is not 0, and unless the mean is 0 and the standard deviation is 1, it is not a z-score. So our first job is to use the formula to change to z-scores. We're looking for the lower number first. It doesn't matter. We'll do it first. 850 minus the mean of 1,029 divided by the standard deviation is 80. The same way we've changed z-scores since we first learned about them. That comes out to be about negative 2.2375. And it said to round it to the nearest hundredth, so I'll go ahead and round it to negative 2.24. And if you want to look at that on the number line, you can see that it's far to the left. Now we do the z-score for the other value, the 900, subtract off the mean of 1,029 divided by the standard deviation of 80, and that comes out to be about negative 1.6125, but again we were instructed at the top to round the z-scores to the nearest hundredth, so that comes out to be about negative 1.61. And looking at that on the graph, we see what we have. We want the area between those two. Well, now we're back to a situation we're perfectly familiar with. We're going to think about the symmetry involved because we're looking at negative z-values. We know the table does not give negative z-values, so we have to think about the symmetry and realize that that area to the left between negative 2.24 and negative 1.61 is exactly the same as the area between positive 1.61 and positive 2.24, and we can look those up in the table. How do we do it? Just like we did in the previous problem. We look up the biggest area, the biggest z-value. And if you look that up in the table, you'll find out that that area is about 0.487. But that's too much area. That takes us all the way back to 0. So what we have to do is look up the area associated with z equal 1.61. That's the excess area that we want to get rid of. So we subtract what turns out to be 0.446 from 0.487, the big area minus the excess area, and that gives us an area of 0.041. It asks us to give this answer as a percent. You have to read the problem carefully and give the answer in the form that you're asked. Asking for a percent means you've got to move the decimal 2 places to the right, so it's about 4.1%. So we can expect about 4.1% of the bulbs to last between 850 and 900 hours. These problems are not difficult, but you do have to practice and then practice some more. Once you get the process involved and the thought processes that you have to go through to come to the right conclusions, you'll find this gets easier and easier. I want to just end this by summarizing these different cases of looking up areas under the standard normal based on what the z-values are. The simplest case is when one z-value is equal to 0. That means the boundary either on the left or on the right is z equals 0. Those are the easiest cases. If the left value is 0, that means the other z value is positive. If the right value is 0, then the other z value is negative. But they're equally easy to solve because of symmetry. Those two areas for the same z value and absolute value are the same. So you really can ignore whether z is positive or negative if one of the values for z is 0. And just look up the positive z value. That's the easiest case, and we've done it numerous times by now. The second case is when both z values are positive or both are negative. In the left-hand case that I've drawn up here, the z values are both positive, and in the second case, they're both negative. But again, because of symmetry, we've learned that we can ignore the fact that they're both positive, both negative, and just pretend that they're all positive. And just look up both z values, ignoring the sign. As long as they both have the same sign, you can ignore the sign, and then subtract the smaller area that you get from the table from the larger area that you get from the table. And again, we've done several of those. You can go back and look if you need refreshing. The third case is when one z value is positive and one's negative. Whenever that happens, that means that z equals 0 is inside the area that you're looking for. And whenever that happens, the strategy is just to break it into two separate problems. Do the value from 0 to the positive z value, look that up in the table and get that answer, and then do the other one, look that up, and then add the two areas together. And again, we've done several of those. The fourth case is when the area is in the tails. Either z is bigger than some value that's positive, or z is smaller than some value that's negative. Those are the tail cases. And in those cases, you're going to subtract from 0.5. The tail value is, in the positive case, to the right of the z value, but the table values give you the area from 0 up to that z value. That's the case where you have to subtract the answer from 0.5. And because of symmetry, the negative case works just the same. You just pretend the z value is positive, look it up in the table, and it'll have the same answer as the corresponding positive one. Those are the four cases. We've gone through each one of them. I just wanted to have one place where you could see all the possibilities in one place. And as you go back and practice more and more, you can kind of look back at this and say, yes, I see, that is how this all works. And again, practice makes perfect on this. The more you do of this, the more it's going to sink in and become muscle memory, and you'll have an easier and easier time each time you do one of these problems.